It is a fact that we all love and use LEDs, and today I want to share to you this simple LED tester I made. Why I built it? Well, after inserting the LED and testing its brightness, the circuit will not only tell me the current but also the voltage drop of the LED, so that I can choose the appropriate resistor when working with it in a breadboard or in a custom PCB. This circuit is also useful to test for efficiency of your LEDs, like look at this old LED. At 5mA its brightness is non-existent, whereas the newer one is way brighter at the exact same current. In this video we will also see the schematic and PCB design of the circuit, so that you can build your own or a modified version of it. If you want to support me, please leave a like and subscribe, or you can also support me through Buy Me a Coffee. The first thing I want you to look at is that this circuit is fully THT. That means I only used through-hole components to build it. This was intentional as I wanted to make it as easy as possible to solder even for beginners. After the soldering process, you can power this circuit with a 9V battery or a 9 to 12V power supply. And using the circuit is pretty easy. Just insert your LED in the correct way and control the current with the push buttons on the left. I've also included a latching push button on the right that cuts the power to the LED, and this board can also test standard SMD LEDs as it has 2 SMD pads, but honestly it's quite hard to test them. Anyway, we can test our LEDs with current ranging from 100 microamp all the way up to almost 50 milliamp, so that we can test either the old inefficient ones and the new super efficient LEDs. Before going into the schematic, let's see the idea behind the circuit itself. We want a way to test our LED by passing current through it, so the best way to do this is to build a current source, and we want to control the amount of current using analog voltage. So what we want is basically a voltage to current converter. To generate the voltage we can use everything we want, but to have precise control we can either use a DAC, or what I actually use is a filtered PWM output of our Arduino Nano. Now let's review the full schematic together. We start with the input power that can be either the 9V battery or the power supply. We have the power switch followed by a Schottky diode to prevent reverse polarity. And we have a capacitor. We then have our Arduino, in which I've tied the push buttons to some digital pins, which are scanned like a keypad. And I'm choosing this approach because we have plenty of pins we can use, and in this way we don't have to put the pull-down resistor into the board. I've tied to SDA and SCL the OLED, which we use to display set current and voltage drop. Then we have the PWM tied to D9, and the drop is sensed with analog A3. The PWM signal goes to this RC filter, and those are just random values. The important thing is that 1/2 pi RC gives you a fairly low frequency. Anyway, the output is then buffered and then divided by 10 using this resistor divider. And this is our voltage input that then will be converted into current. To understand the rest of the circuit, let's suppose we have 2V at the output of the first operational amplifier. After the divider we have 200mV. And so, because the operational amplifier wants its input to be equal, it will control the gate of the MOSFET in order to have 200mV on the inverting input, which means 200mV on this 10 ohm resistor, and so we have 20mA of current flowing through our LED. The selection of the operational amplifier is critical, as it needs to be rail to rail, and if you want your current source to be somewhat precise, you also need it to have a low offset. So I've chosen this LMV722. Up there the J3 connector is just a placeholder for our SMD testbed, and J2 is our through-hole test connector, in which we have tied the Arduino pin to sense the voltage. As the last switch 2 is our latching switch. I think that's all. Let's review the PCB design. Okay, so first this is a simple 2-layer board. On the bottom we have a full ground plane, and on the top we have all the signals and power traces. The bigger traces are 1mm, whereas the smaller ones are 15mm. And there isn't really much going on here. Just follow your basic rules. Don't use too much thin traces. Always leave a good amount of clearance between pattern traces. In my case, I've set the clearance and thread width to 7.5mm, which every manufacturer can easily do. And don't route your traces too close to the edge. I mean, just follow basic PCB design rules. I also made a second version of the PCB which doesn't use push buttons, but instead it uses 16 position coded switch with fixed current values. And since we all make mistakes, I totally forgot to add pull-down resistor for the switch, which I then fixed using a 10K 4-channel SIP resistor network. The schematic is pretty much the same as the other one, we just have the coded switch instead of the push buttons, and here I later added the resistor network, which we can also find in the PCB design. And to get the PCB manufactured, you can install the PCBWay plugin, and with a simple click you are on the PCBWay website. You can see we have the preview of our PCB, you can select the quantity, the thickness of your PCB, the minimum track and spacing used, and other stuff. But for this PCB, except for the color, you can use the default settings. Although I suggest to change the surface finish from the one-way LED to the LED-free one, as it doesn't change the PCB cost and it's better for the environment. You can also get the board assembled, and to do this you need the bill of material and the Centroid file, but you can find all the files on my GitHub page. And if you want to support me, you can buy it directly from the shared project of PCBWay, either assembled or not assembled. Okay, now let's see how precise the current source is by sensing the voltage across the resistor. So let's first try with 100 microamp, and you can see we have 1 millivolt, 2 millivolt, 3 millivolt, 4 millivolt. You can see it's pretty precise. Let's go all the way up to 10 millivolt or 1 milliamp of current. And there we go, pretty precise, you can see. Now let's go with 1 milliamp steps. So you can see 3 milliamp, 4 milliamp, 5 milliamp, 50 millivolts, as you can see. There we go, 60 millivolts, 70 millivolt, 80 millivolt, 90, and there we go, 100 millivolt. I think that's enough for current. Now let's see how much precise is the voltage reading here. So let's put a standard current, for example 5 milliamp. See, we have 1.9 volt on both of them. Let's test another LED. Let me pick a yellow one. There we go. Let's turn on. Again, see, 1.97 on both of them. Let's choose a green one. There we go. See, 2.68, or, well, I don't want to read that number. It's good. Then let's try with a blue one. See, 2.72 volt. There we go. Oh, bloody. Okay, 2.72 volt. Let's try with a white one and 2.77 volt. There we go. Let's try to raise the current to see if it matches even when we're rising the current. And, well, I think it's good enough. Okay guys, that's all for today. Thank you for watching, subscribe, and see you next time. Bye.